This is the fifth lecture in the Chemical Reactions and Chemical Equations unit. Make sure you have your notes handy. If you have the help sheets that go along with this unit, please get those out. And you also need a periodic table to refer to. We've been looking at types of chemical reactions. We've found 4 patterns so far. We're going to look at one more pattern today called hydrocarbon combustion reactions. Now these 5 patterns won't fit every type of reaction you run into, but this will get you a long way in general chemistry. So hydrocarbon combustion reactions are an important part of our human technology. In any combustion reaction, an element or a compound reacts with oxygen. Quite often, you will witness the release of heat and light, and if in those great enough quantity, you may see fire. But combustion reactions can also be slow, and you may not be able to see anything. We saw magnesium combusting with oxygen in an earlier lecture. This is a form of a combination reaction, and so we don't need a new category for that particular combination or that particular combustion reaction. But a hydrocarbon is a little bit different. A hydrocarbon is, as its name implies, a compound made of hydrogen and carbon. There are lots of them that are present in your everyday life. Methane, also known as natural gas, is commonly used to heat homes or water heaters, or maybe even if you have a stove at home that uses gas, it might be methane. If you have a barbecue grill outside, or if you live out in the country, you might be burning propane. If you've ever seen a lighter, that might use butane. And of course, gasoline is a very common example of a hydrocarbon that we use in our everyday life. So let's take a look at the simplest of the hydrocarbons, methane, first. Methane is CH4. This is the gas that we burn in our Bunsen burners in our chemistry lab. In a combustion reaction, oxygen is one of the reactants. Oxygen does not burn, it burns other things. So in this case, methane is burning. By reacting with oxygen, it's releasing a lot of heat and light. We don't write those in our chemical equations because we're only interested in substances at this point in our chemical education. The products of this reaction, if the reaction is complete, are carbon dioxide and water. Here's a picture of a propane grill. If this were set on fire, propane, which is a hydrocarbon with the formula C3H8, reacts with oxygen molecules and produces carbon dioxide and water. You might notice a pattern. Our reactants are a hydrocarbon and oxygen. Our products are carbon dioxide and water. So this pattern does not match any of our previous categories. That's why we set hydrocarbon combustion reaction out as a type of its own. If you wrote this in letter form, you might say that any number of carbons and hydrogens bonded together can react with oxygen. The products of a complete combustion are carbon dioxide and water. The same general pattern can be found for other carbon-containing compounds such as the alcohols. They have oxygen in addition to carbon and hydrogen. The products are still carbon dioxide and water if the reaction is complete. Although you may witness these as being on fire and having a sudden release of energy, they can also take place slowly. Sugar, for example, can undergo a hydrocarbon combustion reaction in your cells and release a little bit of heat, but also provide energy for us to live. you'll notice that the products of the reaction of sugar and oxygen are carbon dioxide, which is why we have to breathe that out, and water, which is why we frequently have to go to the bathroom. I've used this word complete combustion several times. We are going to assume complete combustion in the examples in this video, but I want you to understand that in real life, sometimes you get what are called byproducts. You might have incomplete combustion or incomplete burning, in which case you might get other things like carbon monoxide, which of course is poisonous, or maybe just some black smoke. That's carbon soot. Carbon monoxide, by the way, is not very good for you, so you don't usually have a fire indoors unless you have excellent ventilation. So if your fireplace has a flue, you got to make sure it's open and free of debris. Some people think that Edgar Allan Poe, for example, was cooped up in a room with a coal-fired stove and probably suffered from chronic carbon monoxide poisoning, which among other things causes confusion and delusion and may explain why he wrote some pretty crazy stories. So here's an example of a combustion reaction that I want you to just follow me and I will help you through it. First thing that we notice is that it's a hydrocarbon, C5H12, reacting with oxygen. So the complete combustion products should be CO2 and H2O. Now if we want to balance this, we want to make sure we're very organized and write everything down. Let's make a list. We'll put C, H, and O in order on the left, and we'll put C, H, O in the same order on the right. If you do it in this order, in alphabetical order, then the count on the right will always start 1, 2, 3, which makes it a little faster to do these reactions. So now we look on the left side, we have 5 carbons, 12 hydrogens, and 2 oxygens. I suggest you start with carbon, and we multiply the right side by 5. That will give us 5 carbons. We could go ahead and count the oxygens, but let's hold off just for a moment because I see that when we change water, we're going to change the oxygen number again. So there's no need to count them until the end. So how many water molecules do you think we need? That's right, we need 6 in order to give us 12 hydrogens. Now if we count the oxygens, we get 5 times 2 for the carbon dioxide and 6 times 1 for the water. That's 10 plus 6, which is 16. There are 16 oxygens on the right side of the equation. That's a pretty easy fix on the left side. We just need an 8 as a coefficient in front of our oxygen molecule. And if we double check, we should find 5 carbons on both sides, 12 hydrogens on both sides, and now we have 16 oxygens on both sides. The C5H12 does not have a coefficient, so this is the lowest possible ratio, and that is the answer to the question. Here's a second equation, and what I'd really like for you to do is pause the video and give this one a shot. See if you can do it. But I will warn you that this one is a little bit harder than the first. Go ahead and pause the video, try it for yourself, and when you come back, I will show you how to balance this equation. So we're going to make our count, CHO on both sides. We have 10 carbons on the left, 22 hydrogens, and 2 oxygens. On the right, we have 1, 2, 3. Let's start with carbon like we did last time. Put a 10 in front of that carbon dioxide. And let's put an 11 in front of the water. But now we run into a little problem. if we add up our oxygens, we're going to have 10 times 2, which is 20, plus 11 times 1, which is 11, and 20 plus 11 is 31. That's an odd number. And the reason why that's a problem is because on the left side of the equation, the only substance that has oxygen in it is O2. Since there's a 2 there, it's always going to be even. There's no way to get an odd number of oxygens on the left side. That means we need an even number of oxygens on the right side, which means we picked the wrong coefficients. But it's a pretty simple fix. All you have to do is double the coefficients that you just picked. If we put 20 instead of 10 for carbon dioxide and 22 for water instead of 11, we will now have 62 oxygens. You can count for yourself, but it's 31 times 2 if you remember their number from before. But it's 20 times 2, which is 40, plus 22 times 1. 40 plus 22 is 62. Now we can fix that on the left side by multiplying oxygen by 62 divided by 2, which is 31. Now we have a balanced chemical equation. Or do we? We don't. Don't rush. Always do your double check. It turns out we need 20 carbons on the left, so I need to put a 2 coefficient in front of the C10. That will also give me 44 hydrogens. Now I should have the same number of each element on the left and the right. So it's time for you to do a little practice. Hopefully your teacher has given you a worksheet to work on. If not, I'm sure that you'll find plenty of problems out there on the internet. Or you know what? Here are some problems that you could work on. This is what I call mixed practice, meaning that this could be any of the 5 types of reactions. So in the first blank, see if you can identify the type of reaction that's taking place. Is it combination, decomposition, single replacement, double replacement, or hydrocarbon combustion? Then in the other blanks, see if you can supply the coefficients that would balance these equations. And there's one more set of mixed practice problems. In this one, we're going to go one step further. In addition to identifying the type, I want you to see if you can actually predict the products and write their correct formulas. So first identify what type of reaction is taking place, then do the appropriate action to follow that pattern, write the neutral formulas, and then balance with coefficients. Once you get neutral formulas, don't change your subscripts. Use coefficients to balance only after neutralizing. Good luck!